Hello everyone. Uh, Last time, if you remember, we were studying what are TLBs, translation local site buffers. Okay? So we are left off the chapter before the end. So in this video, I will complete that chapter from. I will take up the discussion from where we had left off. Now, what are TLBs? If you remember, the problem with paging was that paging was too slow. It was making the performance of our programs too slow because for every memory access, we had to access the memory twice. Once to access a page table because we needed the page frame number to convert the virtual address from to physical address. Okay, so for this virtual to physical conversion, we needed the page frame number, which was stored inside the page table, and the page table for every process was stored in RAM. Okay, so one memory access was needed to convert virtual address to physical address, and then once we had the physical address, then we made another memory access to RAM to read our actual data that we originally wanted to read. Okay? So every memory access in this paging mechanism was resulting in two memory accesses, and because of that, our program would have run very, very slow. So as a workaround to that problem, the system designers came up with this solution that although we cannot store all of the page tables inside the processor because the size of the page tables is quite big. Okay, so we don't have enough space inside the processor. But what we can do is that we can have a cache for frequently accessed page table entries inside the processor, and that cache for frequently accessed uh, page table entries, we call it TLB, translation local site buffer. Okay? So what a TLB essentially is that it's a cache that contains mapping from virtual page number to physical frame number. Okay, and these recent mappings are stored inside the TLB. Okay? And since TLB has only a limited space, it's a very, very small cache in terms of number of bytes. So we can put it on site on the processor. Okay, and what happens is that next time when your program is going to access a memory location, while converting its virtual address to physical address, it will first look up the virtual page number inside a TLB, okay, to see whether it can find the entry for that virtual page number inside the on-chip TLB or not. If it finds the virtual page number entry inside the TLB, then from that mapping in that entry, it will automatically get the physical frame number. Okay, so all this process happened on the processor inside the TLB cache, and the program did not have to go to access RAM or access the page table inside the RAM for this virtual to physical conversion. Once you have the physical address, then you can go and access RAM for actual reading actual data. So if you see this process, in this process we accessed RAM only once, okay, because for virtual to physical conversion, we needed the page frame number, which we found inside the TLB. Okay? For that, we did not have to go to RAM. So that RAM access was avoided thanks to TLBs. Okay? So this process, when we find our desired virtual page number inside a TLB, we call it a TLB hit. Okay? So in case of a TLB hit, your memory access will be fast because you will be accessing memory only once. What if there is a TLB miss? So if there is a TLB miss, which means that your program wanted to access a memory location, it had the virtual address, it searched for the virtual page number inside a TLB, and it did not find the desired virtual page number inside any of the TLB entries. Okay, so this situation will be called a TLB miss, and in case of a TLB miss, then we'll go access the RAM, and inside RAM we'll access the particular page table of our process, and inside that page table we'll find the corresponding page frame number for that virtual page number. Okay, and then our virtual to physical translation would happen. So this will access RAM once for the page table, and then once you have physical address, then we'll access RAM the second time to read our actual data. Okay, so in case of a TLB miss, we will be accessing RAM twice as we were doing before the TLBs. Okay? But the key insight here is that our programs are localized in their execution. They have temporal locality and spatial locality. So at any given moment, they will be accessing any particular data, a set of data and a set of code. Okay, they will not be needing all their code and all their data at the same time. So what happens is, even if there is a TLB miss, during that TLB miss, when we go and read the page number from the page table in RAM, we will also update the TLB to include this new mapping of this virtual page number and this page frame number, physical frame number, inside the TLB. So due to locality, our program will most probably access this virtual page again. Okay? And then the next time, since we have just updated the TLB with this mapping, we will find the virtual page number inside the TLB, and we would not have to access RAM again. Okay? So as long as this mapping of virtual page number and physical frame number is inside the TLB, our program will get TLB hits, and we will be accessing RAM only once for our memory accesses. Okay? So this all we had studied in the last class, and we had seen this example that, let's say we have an array of integers which is stored like this inside our virtual address space. Okay? So it spans multiple pages, multiple virtual pages, and it goes from page 6 to page 8. Okay? And each virtual page here is of 16 bytes. So when our program accesses this array first time, then there will be no TLB entry for this array or these pages inside the TLB. Okay, so let's say the program wanted to convert this virtual address of A0 from virtual to physical address, then it will go and look up the physical frame number for page number 6. It will go first look inside the TLB. It will not find the entry inside TLB because this array has never been accessed before. So what it will do is that it will go to RAM and look up this virtual page number entry inside the page table for this process, which is stored inside the RAM. Okay? It will get the physical frame number and then update the TLB with this new information that virtual page number 6 is residing in this physical frame number. Okay, so TLB will be updated with this information, and then the program will access this array A0 again, and it will find the memory location, the TLB entry inside the TLB, and it will convert the virtual address to physical address, and then it will go on and access the actual data from the RAM. So to access A0, we have accessed RAM twice. Once to read the page frame number from RAM, from the page table, and second time to read our actual data from RAM. So for A0, there was a TLB miss, and we had to pay the penalty of accessing RAM twice. What about when we access A1 immediately? Just like in this loop, we will be accessing all the array elements successively. So when we want to access array 1, we'll have to convert its virtual address to physical address, and it lies on the same page as A0, so page number 6. So to convert this address to physical address, the system will first go and look up this virtual page number 6 inside the TLB. And since we had just updated the TLB for accessing A0, this access of A1 will also find this page number 6 inside the page table entry, inside the TLB entry. So it will directly access the physical frame number from the TLB entry and will not go to access the page table in RAM. Okay, so this for A1 there was a TLB hit, and once we have the physical frame number, we convert its address to a physical address and go access the actual data from RAM. So for A0 there was a TLB miss, we accessed RAM twice, but for A1 we saw that there was a TLB hit and we accessed RAM only once. Similarly for A2 there will be a TLB hit, okay, because this entry for page 6 is stored inside the TLB, still stored inside the TLB. Next, when we access A3, the entry for page 7 is not inside TLB, so again for A3 we'll get a TLB miss, we'll access RAM twice, but for A4, A5, A6 we will get TLB hits. Okay. So similarly for A7 there will be a TLB miss, but for A8 and A9 there will be a TLB hit. So we can calculate from here that what is our TLB hit ratio. Okay. And here it's about almost 1 out of 4 accesses is a miss, so TLB hit ratio will be about 75%. But you can imagine by looking at this figure that if our page table, our sizes of our pages were large, then we will have more TLB hits on the same page. Okay, so our TLB hit ratio would be higher. So that's about this the accesses that we discussed. For every access, we'll get these virtual addresses, and then we'll either get a TLB hit or TLB miss. This is the thing that we just discussed. So you can see by looking at the figure that in case of locality, when we are our program is accessing some data that is close together, we will be getting lots of TLB hits. So TLB hit rate we already concluded, and also the effect of page size on TLB hit. One other thing that we discussed at the end of our class was that when there's a TLB miss, we have to go access the page table entry in the page table in RAM, get the physical frame number, and then we have to update the TLB with this new entry or this new mapping that we just accessed from the page table, that this particular virtual page number maps to which physical frame number. Okay. So this updating of TLB, which part of the system does it? Okay, is it done in hardware or is it done in software? So we had discussed that there are two approaches to designing computer processors, the two main approaches. We can classify them into this CISC and RISC approaches. Okay. CISC basically stands for complex instruction set computer, and RISC stands for reduced instruction set computer. Okay. So the concept in CISC is that we make complicated, powerful hardware so that our software should be easy to write. The RISC approach is that we make our hardware simple, okay? Because complex and powerful hardware, as the name indicates, it would be complex and there will be more probability of having bugs, and it will be difficult to debug that hardware. RISC basically is the opposite approach, in which we keep our hardware simple and let the software do most of the work. So since in CISC the approach is to go for powerful hardware, then in CISC we will find that this TLB update happens inside the hardware, okay? Inside the MMU. When the MMU converts virtual address to physical address and it sees that we have had a TLB miss, then the hardware circuitry inside the MMU, it would go read the page table in RAM, get the physical frame number, and update the TLB with the virtual page number and physical frame number mapping that we had just discovered. Okay. So this thing happens in RAM, in hardware in CISC. In RISC, since we are trying to keep our hardware simple, so we delegate this task of updating the TLB to software or to the operating system in particular. Okay. So when there is a TLB miss, the MMU does nothing but it raises an OS exception. Okay. So the OS exception handler will run, and then that exception handler code, which is basically software code, it would go access the RAM, read the physical frame number for this particular page number, and update the TLB with this new mapping of virtual page number and physical frame number. Okay, and then it would return from trap or return from exception, and then it would execute the instruction which caused this exception again. Okay, so next time this exception is executed, the MMU will find the physical frame number inside the TLB, and it would not raise an exception, and the execution will continue forward. Okay, so this is how TLB updates are handled in CISC as well as RISC architectures. Yeah, so this return from trap is different from the return from tap that we read in the case of a system call in the first few chapters, because the return from trap of a system call will start from the next instruction. Okay, but the return from trap would execute the same instruction again, because that instruction that raised the exception in case of a TLB miss has not finished executing yet. Okay, so when we return from trap for this TLB update, we will basically re-execute the instruction that raised the exception, so that now this instruction will find the entry in TLB and it would execute, and then execution will move forward. So again, what if the instruction that accesses the page table for page frame number results in TLB miss? You see, the TLBs, sorry, the physical, the page tables are also stored in RAM. Okay, so if we map page tables also to virtual addresses, then what can happen is that for every virtual to physical address translation, we will basically translate the virtual address to physical address, and for that we will do a lookup in the TLB. So let's say you had a normal instruction that wanted to access memory, and to convert its virtual address to physical address, you did a lookup in TLB, you did not find the virtual page number, and you raised a TLB exception. Okay, so the OS exception handler runs, and then it wants to the exception handler wants to access the physical frame number in the page table. Okay, and now if the addresses of the page table were also virtual addresses, then to access a page table in RAM, this OS exception handler code would also do a conversion from virtual to physical address, and for that it will first look up inside the TLB. And what if the page table and the TLB entry, there is no TLB entry for the page virtual page number of the page table inside the TLB. So it would again result in a TLB exception. So again, the same exception handler will run. So it will again try to get the physical frame number for this particular page. Again, it would not. It will try to convert the virtual address to physical address. Again, doing so, it would do a TLB lookup. Again, it would cause a TLB miss. Again, it would raise an exception, and again, the same exception handler will be done. So it can result in this infinite series of TLB misses. So to avoid this situation, what the system designers do that to ensure that there is no TLB miss in accessing a page table, if they are using virtual addresses for page tables, what they would do is that they would reserve some entries of the TLB for page table entries. Okay. So the virtual page numbers of page tables would always reside in the TLB. Okay. So there will be no miss when accessing virtual page page numbers for page tables inside the TLB. Okay. This is one solution. Another solution could be that you reserve a physical area of RAM for the page tables and do not use virtual addresses for page tables. Okay, so when accessing page tables, we would not do a virtual to physical address conversion, and we would directly access RAM to access the page tables. So these two solutions are mostly employed to avoid this situation. So what does a TLB look like? What is inside a TLB? So a TLB basically is a table, or we can say it's an array of TLB entries. Okay, and each TLB entry looks like this. Okay? In each TLB entry, we would have these kind of information. First of all, we will have a mapping from virtual page number to physical frame number. Okay, we would reserve some bits of the TLB entry for the virtual to store virtual page number, and some more bits of the TLB entry to store the corresponding physical frame number for this particular virtual page. Okay, so we'll have this one-to-one mapping of virtual page number to physical frame number, and then we would some extra information bits. Okay. So what's in these extra information bits? These can have different information about these pages whose entries are stored inside the TLB. So what kind of information do you have? First of all, there's a valid bit. There's a valid bit that says whether this particular TLB entry is valid or not. Okay. So let's say it's the first time your program is running, and it is going to do a virtual to physical address translation. It will go and look up inside the TLB. Now the TLB, since this is the first time this program is accessing the TLB, so all the information in the TLB is garbage for this program, because there is no information related to this program inside the TLB, because all this information that would have in the TLB entries this page number, frame number, other bits, etc., that would be from the previous programs. Okay. So the valid bit for all these entries would be 0 for this new program, because these information are not for this program. Okay, so valid bit basically tells the program whether these TLB entries are valid or not. Valid means they can use it or not. So this program, for the first time, when it accesses this page table entry, TLB entry, even if the virtual page number matches with the virtual page number of the address that the program is looking, there will be still a TLB miss, because the valid bit will be 0. Okay, and that would be correct, because this information, virtual page number and physical frame number, is for the previous process. Okay, so the current program cannot use the information of the previous process. So there will be a TLB miss, and then the program will go into RAM, read its physical frame number, and update this TLB entry, and it would set the valid bit to 1, so that the next time it accesses this page number, it would find a TLB hit. Okay, so a valid bit tells you whether this particular TLB entry is valid or not, which means you can use it or not. Then there are protection bits. Some bits, in Linux-like systems, there are protections for users and groups, etc. For example, you could have protections of read, write, and execute. Similar protections apply to uh, pages. Okay, so you can have 3 bits for each page, which will tell you whether this page can be read or not, whether you can write on this page or not, or whether you can execute the code on this page or not. So these protection bits are to provide some kind of security, so that you do not write to pages for which you do not have access. Similarly, there is a dirty bit. A dirty bit basically is an indication whether this page, when it was, since it has been brought into memory, has it been modified or not? Has it been written to or not? Okay. When we allocate a page in RAM, we'll bring in data from hard disk or from other source inside that page. So as long as we do not modify, or our program does not modify the data in that page, dirty bit for that page would remain 0. Okay. But when we modify the data in that page, when we write something or some data inside that page, then that dirty bit for that page will become 1, indicating that since the last this page has been brought into RAM, it has been modified. Okay, that data has been written to this page since it has last been brought into RAM. Okay, so dirty bit tells you whether that page has been modified or not. Then there are some other bits. We can have some other bits inside these page table entries. For example, address space ID. So address space ID, let's see it on the next page. Let's say there are 2 processes running in the system, P1 and P2, and let's say it's a single core processor that we have. It can run only one process at any given time. So the virtual page numbers for all processes are the same. Okay, as you guys know, the virtual addresses for all processes are the same, because each process has the same illusionary view of the virtual address space. So P1 and P2, they both have some data in their virtual page number 10. But the virtual page number 10 of P1 is mapped to physical frame number 100, and the virtual page number 10 of P2 is stored in physical frame number 170. So whenever there is a context switch, a new process will come and start running. Okay, so P1 and P2, they will both be switching and running on the processor. So at some time, both of them will access their virtual page number 10. Okay, and if we do not take care, we will see that we would have both these entries inside the TLB. That virtual page number 10 is stored in frame number 100, and virtual page number 10 is stored in page number frame number 170. Okay. So let's say one of these processes is currently running, and now it wants to access its page virtual page number 10. It goes and looks inside the TLB. Now inside the TLB there are two mappings for virtual page number 10. So how would this process know whether it is P1 or P2? It doesn't matter. But how would this process know which of these entries is mine, so that I can take this frame number and convert my virtual address to physical address? So how will this process know? Right now, as it is, there is no information in this TLB that which page table entry belongs to, which TLB entry belongs to which process. Okay, which process is use which TLB entry. There is no information here. So one thing could be that whenever there is how do we solve this problem? Okay? So there can be two solutions. One solution can be that whenever there is a context switch, we make the valid bit of all these entries 0. Okay? So that the next process can come and it will, when it tries to look for page number inside the TLB, it will see that valid bit is 0 for all these, so it doesn't use any of these entries. It goes inside the RAM, accesses its page table, and then gets the page frame number, updates the page, TLB, and then accesses the physical address that it will obtain from converting the virtual address to physical address. Okay? So in this situation, for every context switch, we invalidate all the page, TLB entries, and the next process that has started running as a result of this context switch will have a lot of initial TLB misses. Okay, but at least its execution will be correct. It will not be confused by this kind of situations. Okay, so that's one solution that is very simple, but it's a little expensive, because for every context switch, the new process that has started running will have lots of TLB misses. The information that was useful was inside the TLB, but was invalidated because of making this valid bit 0 at context switch. So that's one solution to correct the problem of these which table entries belong, TLB entry belong to which process. We simply invalidate all entries, and the new process will build its TLB entries from 0 after a lot of misses. Okay. So we call this flushing the TLB. It is costly, as I just explained. Another solution is to use these address space ID bits inside each table entry. Okay. So what address space ID bits are, that they are identifying the process. Okay. For example, when there are multiple two processes running and both are accessing their page table virtual page number 10, so their entries would be stored in the TLB, and for the same virtual page number 10, we have two different physical frame numbers. That's because they belong to two different processes. So the address space ID bits will tell to which process this mapping of virtual page number to physical frame number belongs. Okay. So let's say for P1, this value is 1, and P2, this value is 2. Okay. So when each of these processes is running, it will have its address space ID stored somewhere inside the processor, inside the MMU. Okay. So when it wants to convert its virtual page number 10 to physical frame number, then using its virtual address space ID, it will see that which of these entries is its own, and it will use that particular entry to convert its virtual page number to physical frame number. Okay. So this is another solution which is costly in a sense that you have to extend your TLB entry, you have to modify your hardware to make space and add circuitry for looking up this address space ID. Okay. But the benefit or the upside of this solution is that at every context switches, we don't have to invalidate the whole page table, and the older page table entries still remain inside the page table, and the next time this process is scheduled again, it will find its old mappings inside the TLB, and they will reduce its number of TLB misses. Okay. So in this sense, this situation is more efficient. So this is I mean, an example of how a TLB looks like. What's inside a TLB entry? These are the protection bits that we discussed. Read, write, execute for each page. So one thing that we have to see is that how does uh, the MMU perform a lookup inside the TLB? How does it determine whether this particular access is a TLB hit or a TLB miss? Okay. In page tables, if you remember, page tables are an array in which indices are the virtual page number and the value at that index is the physical frame number. Okay. So lookup in page table is very easy because we have the virtual page number and that serves as an index, and we directly go read the value at that index and get the physical frame number. In TLB, it's slightly different because TLB is an associative cache. It means there is no order of entries inside the TLB. So given a virtual page number, we cannot directly go and look up one particular page table entry. Okay, because associative cache means there is no order or there is no order in the storage of values inside the TLB. Any mapping of virtual page number can be stored at any location in TLB. So for that, in our hardware, what we have to do is that to do a TLB lookup, when we are given a virtual page number, we have to compare that to all the entries inside a TLB. Okay, and we'll see to which entry it will match. So a TLB lookup is different from page table lookup. In page table lookup, we do not search all the page table. Okay, we access that page table entry directly. In TLB, we have to look up all the page table and all the TLB entries and compare the virtual page number to the virtual page number in all of these TLB entries, and then we'll see if we find a match, it's a TLB hit, and if it does not match, then it's a TLB miss. Okay. One other problem is that what happens when all the entries in a TLB are full and a new one arrives. If you remember from the past slide, the number of TLB entries is very small. Okay, there are 32, 64, 128 entries inside the TLB. And this fully associative is what I just described, that to do a lookup in TLB, we have to search all the entries inside the TLB. So if you have a limited number of TLB entries, then with each TLB update, a new entry will be put in the TLB in a free slot, and very quickly the TLB will become full. Okay. So once the TLB is full, okay, and you have to update the TLB again, a new TLB entry arrives. So how do we update the TLB now that it is full? There is no empty space inside the TLB. We'll have to forcefully replace one of the TLB entries. Okay, overwrite one of the TLB entries with this new one. So the decision which entry we can overwrite. How can we choose which entry will be overwritten by this new entry? This process is called replacement policy. Okay. So replacement policies for TLB entries, there are different. If you guys have studied caches, these are basically the same replacement policies that are used in caches. It can be an LRU policy. LRU stands for least recently used. Okay. Because we have discussed, because of temporal locality, recently used data would be used again, is greater probability that it will be used again. So the least recently used entry is least likely to be used again. Okay, so we can replace the least recently used entry with this new one. Okay. So for that, we have to keep track of inside a TLB the order in which these TLB entries were accessed and which one is the least recently used. Okay. So we'll select the least recently used and overwrite it with the newly arrived TLB entry. So LRU is one replacement policy. Another replacement policy is random, where we can choose random bits, random entry from the TLB and replace any random entry. This is another replacement policy. It's simple to implement because for LRU you have to keep track of which is the least recently used entry inside the TLB. But in random, we do not have to keep track because for every new TLB entry, we'll replace a random entry inside the TLB. So there is another also sometimes which is cited replacement policy. It's called FIFO, first in, first out. So whichever basically came first should be overridden first. Now, LRU replacement policy can have a flaw that if your loop has n plus 1 pages, you are accessing n plus 1 pages in a loop, and the page table has only n entries. Then when you start populating the page table, the first entry will be a miss. You will update the page table. Second access to a page, second page will be also a miss. Access to a third page will also a miss. So you are accessing all these pages one by one, and you are updating the TLB entries, and all these accesses are resulting in TLB misses. So you fill all the n entries of the TLB. Next, when you access the n plus 1th page in the loop, so you will have to replace one of the entries in the TLB because all n entries of the TLB have been filled. So the LRU will basically replace the first page that you stored in this TLB or the first entry that you updated in this TLB. So it will overwrite this first table entry. The next loop will start again, and it will again access all these pages in the same order. So it will start from the first page, and since the first page you have just overwritten it, so the first page will again return result in a miss. For that, you will bring in the mapping for the first page again, and what you will do is you will replace the least recently used, which will be for page number 2. So you will overwrite the page number 2 with page number 1 entry, and then loop will access page number 2 again because it's accessing all the pages in sequence, and page number 2 has just been overwritten, the entry for page number 2, and it will again result in a miss. And to bring in the entry for page number 2, you will overwrite the least recently used, which will be for page number 3. Okay, and then you'll just after updating the TLB, your loop will access page number 3, whose entry you have just overwritten. So it will result again in a miss. So this is a pathological case that can arise in LRU policy. Okay? Random policy is not affected by this. So here it's a page table entry for the hardware of a real processor, an old processor called MIPS R4000. Okay? It has a 32-bit address space and 4 kilobyte pages. So let's look how does its page table TLB entry looks like. Okay, so it has a 32-bit, sorry, 64-bit TLB entry, and we can see that the first and foremost purpose of the TLB is to store a mapping from virtual page number to physical frame number. Okay, so for each table entry, for each TLB entry, we'll have virtual page number and its corresponding physical frame number. And then we have the ASID bits that we just discussed in the last few slides, which will keep track of the process to which this page table, this TLB entry belongs. And there are some other bits. V is that valid bit, whether that this particular page table entry is valid or not. D is the dirty bit, and the global bit is 1 for all the pages that are shared between different processes. So for that, if the global bit is 1, then ASID bit is ignored because this page is common to all the processes. So this is an example of a real life TLB, and that's all for this chapter. Thank you very much. I'll stop the recording now.